Hello, I'm Tom.
And I'm Mia.
Welcome to the Adaptix podcast. You know, this is our series where we turn these really advanced ideas in artificial intelligence and robotics into, well, simple, clear explanations. I mean, we all know this field moves so fast, and a lot of the time it can feel pretty overwhelming. So our goal is just to create a space where anyone, and we mean anyone, can build their understanding at their own pace. Doesn't matter if you're just getting started or maybe you're exploring the broader world of intelligent systems. Let's dive in.
In this episode, we want to talk about the core concepts and building blocks of artificial intelligence and explore how these pieces fit together to create modern AI systems.
Which is such a crucial thing to do right now because AI has become this, this giant catch-all phrase.
Right.
And to really get what's happening, to understand the power and, frankly, the limits of what we're building, you have to break down the parts.
Yeah.
It kind of demystifies everything.
Absolutely. And for so long, AI was just science fiction, right? It was all about making machines think like us.
Mm-hmm.
But that whole idea has changed. Today, when we talk about an AI agent, we're talking about something that just perceives its environment and takes action to succeed. It's all about function, not feeling.
That functional shift is everything. It means we stop asking, is it human-like? And we start asking, does it solve the problem effectively? I mean, at its core, an AI system is really just an information system. You've got your hardware, software, data. It's all there. And the cycle is classic, input, process, output, turning raw stuff into something useful.
And to get beyond that high-level view, there's a framework that breaks it all down into 6 core building blocks, which is super helpful for, just getting your head around it all.
It's a fantastic map. It really is. These 6 blocks, they define the whole life of information in the system. You start with the inputs, structured data and unstructured data.
The raw materials.
The raw materials. Then you have the prep stage, what we call pre-processes.
Yeah.
After that comes the magic, the main processes. And finally, you need a memory and a way to act.
Yeah.
The knowledge base and the information outputs. That's the blueprint right there.
Okay, let's unpack that, starting at the bottom. The foundation, the data. It sounds so simple, but the sheer amount of it is where the complexity kicks in.
It's everything.
Yeah.
It is the foundation, the quality, the volume of your data that sets the performance ceiling for anything you build. And we usually split it into 2 big buckets.
Right.
First, you have structured data. This is the stuff we're all used to.
Yeah.
It's organized, it's neat, it fits in a spreadsheet.
Like sales figures, inventory.
Exactly. Sales data, inventory figures, stock exchange data that's flying by. It's all in nice, neat rows and columns. AI is great at chewing through that.
But the big breakthroughs, the things we see today that feel like magic, that comes from its ability to handle the other kind, the messy stuff. Unstructured data.
Precisely. And that's most of the data in the world.
Oh, yeah.
Well, it's not standardized. It's hard to analyze. We're talking about, everything on social media, audio files, videos, product reviews.
Right.
The AI has to figure out what's even important in that mess before it can start to count or categorize anything.
Yeah.
And that ability, that's what makes modern AI, modern.
Yeah. It seems obvious that good data is important, but it feels like the impact of bad data is more than just getting a bad result. It seems to create these long-term structural issues.
Oh, it's a huge strategic problem. The data isn't just feeding the model. In a very real sense, the data is the code.
The data is the code. I like that.
So if your data is flawed or biased, you're building up what we call technical debt. And that's a nightmare because the costs are hidden, they're long-term, and it's all about maintenance down the line. It's like writing buggy code that you'll have to pay to fix later.
That analogy really drives it home. So if your data set, say, isn't diverse enough, the model just won't be competent. And fixing that later is, expensive?
It's incredibly expensive and difficult. Imagine you're training a self-driving car. You have to show it everything, not just sunny days, but weird weather, stuff falling on the road, other drivers doing crazy things.
All the edge cases.
All the edge cases. If you only train it on perfect conditions, it's going to fail, maybe catastrophically, when something unexpected happens. The AI's skill set is a direct reflection of the data it eats.
So what do you do then if you're a company and your data just isn't good enough? You can't just give up. What are the strategies to fix that?
Well, the first step is always data cleaning. You can't skip it. It's that initial stage where you're fixing errors, dealing with missing numbers, finding the weird outliers.
Yeah.
But cleaning alone is rarely enough if the data is just sparse.
Okay, so then there's this other idea which I find fascinating. Creating synthetic data. How is that different from just making stuff up.
It's not just making stuff up. It's about modeling the underlying pattern. If your engineers understand the statistics of the data, say how patient age relates to a disease, they can use AI tools to generate a whole new massive data set that looks and feels real.
I see.
This is a lifesaver when real data is hard to get, maybe because of privacy rules, or when you have a huge imbalance, like 10,000 examples of something happening and only 10 of it not happening. Synthetic data lets you balance the scales.
But aren't you running a risk there? If your understanding of the original pattern is flawed, you're just creating more flawed data, right?
That is the critical risk. Absolutely. If your initial model is wrong, the synthetic data will just be a perfect copy of that mistake, making the whole system brittle. It takes a ton of careful validation to make sure your fake data truly represents the real world's variety.
So high risk, high reward. What about the third option, data fusion?
Data fusion is all about combining information from lots of different messy sources to get a single, more accurate picture. Think about intelligence agencies or huge global supply chains. They have to do this. It lets you overcome gaps or inconsistencies in any one data stream.
But trying to combine, social media posts with satellite images and sales numbers, that sounds like a computational headache. When does the benefit actually outweigh that cost?
That is the million-dollar question for managers. Data fusion is always expensive and complex. You're trying to sync up all these different data types. The benefit wins out when the information gain, the reduction in uncertainty you get from combining sources, is absolutely critical for what you're doing.
So for things like autonomous driving or
predictive maintenance on a billion-dollar jet engine. If the cost of being wrong is massive, then fusion becomes non-negotiable no matter how much it costs to run.
That makes perfect sense. Okay, so we've got our raw materials, the data, and we've cleaned it up. That brings us to the next block, the prep stage. Pre-processing. What's the main goal here?
The goal is transformation, plain and simple. The learning algorithms can't eat raw data. So this stage is all about cleaning, transforming, and selecting, turning pixels or sound waves or raw text into structured, usable features the system can understand. You see this most clearly with language and with vision.
Let's start with language. Natural language understanding, or NLU. It's something we do without thinking, but for a machine, it's a huge challenge.
It's a monumental challenge. NLU is how an AI makes sense of what we say or write. The first step is what we call speech recognition, just turning sounds into text. But the really hard part, the core of NLU, is ascribing meaning.
And meaning is so tricky because it's all about context, isn't it?
It's all context. I mean, take the word crane. Is that a bird, piece of construction equipment?
Why?
Or are you, craning your neck to see something? The AI has to figure that out, plus deal with jargon, sarcasm, dialects.
Wow.
So to do this, modern NLU systems use these massive statistical models. They look at a huge window of text, not just the word itself, but hundreds of words before it, to calculate the most probable meaning.
So it's always playing a probability game just based on all the text it's ever read.
It's a very, very sophisticated guessing game. And when it works, you get amazing things like text summarization, where it can read a long article and give you the bullet points, or sentiment analysis, where it can tell if a customer review is happy or angry.
Okay, moving from the abstract world of language to the visual one, we have computer vision. This feels incredibly difficult just from the sheer amount of data involved. Millions of pixels.
It's extremely demanding, the huge computational bottleneck. The goal here is to turn an image or a video into a structured representation the AI can use. And it uses deep learning to recognize incredibly complex patterns.
I've heard facial recognition is at a human level now.
It is. In many cases, it matches or even beats human performance, which is just incredible. The hard part is teaching the system to generalize, to recognize your face, not just in one perfect photo, but in bad lighting, from a weird angle with a different haircut.
And that leads into what feels like the final step of pre-processing, feature engineering.
Yes, and this is where a lot of the art of AI comes in. Feature engineering is the task of pulling out the most important, high-value pieces of information from all that data. If you do this badly, or not at all, the learning process becomes super inefficient. It's just brute force.
So why spend time on that? Why not just throw all the raw data into a giant model and let it figure it out?
That's the trade-off. You can do that, but it takes way more data, way more computing power, and way more time. Feature engineering is like giving the model a huge shortcut. You're telling it, hey, don't worry about all that noise. These are the variables that really matter. You shrink the problem down.
Did you give me that fish farm example again? That really made it click for me.
Of course. So you're trying to design the perfect sustainable fish food. The raw data is just lists of ingredients, chemical data, market prices, very generic.
Right.
A good engineer does feature engineering and turns that into predictive features, like animal requirements, the exact nutrients this fish needs, or animal response, how the fish's body reacts to this ingredient. By giving the AI those refined inputs, it can find the optimal recipe almost immediately, instead of running thousands of expensive real-world experiments. It's a massive gain in efficiency.
Okay, so we've got the perfect data with the perfect features. Now we're getting to the brain of the operation, the main processes. This is where the thinking and learning actually happen.
This is it. And these processes are really built on 3 core intelligent behaviors: problem solving, reasoning, and of course, machine learning. Machine learning is kind of the umbrella that uses the other 2 to get smarter.
Let's break down problem solving first. It sounds like just finding the best answer.
It is, and we see it in 2 main flavors. First is convergent problem solving. That's the search for a single best answer. And with big data and huge computers, AI is just phenomenal at this. Think about optimizing a delivery route for a fleet of trucks in real time.
And the flip side is divergent problem solving.
Exactly. You use that when there isn't one best answer. You need to generate lots of different creative options. This is where AI gets into design, for instance. It could generate 100 different chair designs that all meet your basic criteria.
Yeah.
Or it could brainstorm different scenarios for a financial risk model.
Okay, next up is reasoning. This sounds more like formal logic.
It is. It's about applying logic to information, even when you're not totally sure about the information itself. And we generally talk about 3 main forms of it.
Let's start with the most straightforward one, deductive reasoning.
Deduction is top-down. You start with a general rule you know is true, and you work down to a specific conclusion that must be true. It's the classic syllogism. If all men are mortal and Socrates is a man,
then Socrates is mortal. Guaranteed.
Guaranteed. If the premises are true, the conclusion is certain. It's very powerful, but it's limited because you can only conclude things you basically already knew.
Right. It doesn't discover anything new. Which brings us to the engine of discovery, inductive reasoning.
Inductive reasoning is the opposite. It's bottom up. You see 1,000 white swans one after another, and you make a general rule. All swans are white.
Ah, but that conclusion isn't guaranteed.
It's not guaranteed. It's just probable. You might see a black swan tomorrow. But, and this is the key point, this process of creating general rules from specific examples, that is the absolute core of how machine learning works.
So machine learning is basically a giant induction machine.
That's a perfect way to put it. It's constantly looking at data and trying to induce the rules. Which brings us to the third type, abductive reasoning. This one's the detective logic.
Sherlock Holmes.
Exactly. You start with a set of observations, the clues, and you infer the most plausible explanation. The conclusion isn't certain, it's not even necessarily probable, it's just the best guess you can make. It's what doctors do during diagnosis. It's about generating a good hypothesis.
So we've got deduction for certainty, induction for learning, and abduction for explaining. Now let's tie this all together with machine learning itself.
Right, so ML is what lets the system get better over time without a human having to write new rules for it. Early ML was very guided. You tell the system exactly what to look for, but that was really limiting.
And that's what led to the big leap into what we now call deep learning.
That was the transition. It happened when we built algorithms that could find their own interesting features and knowledge from these huge piles of data. And deep learning, which usually means using artificial neural networks, or ANNs, is what lets the system solve much, much more complex problems. It discovers things no human would have ever thought to program.
For someone listening, how should they picture an artificial neural network? The name sounds so complicated.
The best way to think about it is not as one big brain, but as a series of simple stages or layers stacked one after another.
Okay.
Each layer just does a really simple little calculation on the output of the layer before it and then passes its result on. The power doesn't come from any one calculation. It comes from having hundreds or thousands of these simple layers working in a cascade. That's what lets it map incredibly complex inputs to outputs.
It's the emergent complexity, which brings us to the big theory behind why this works so well, the universal approximation theorem.
We have to pause here because this is the theoretical bedrock of deep learning. The theorem, in simple terms, says that a neural network with just one hidden layer, as long as it's wide enough, can approximate any continuous mathematical function.
That's a huge claim. So it can learn literally any relationship in the data, no matter how weird or complex.
Any continuous relationship, yes. Think of it like a universal sculpting tool. You can give it any shape, and it can replicate it. And it gets even more powerful. When you add memory to the networks, creating what we call recurrent neural networks, they become Turing complete.
Meaning they can compute anything a regular computer can compute.
In theory, yes. They can simulate any algorithm. So the theory tells us the architecture has almost unlimited potential.
Which flows perfectly into the different ways these networks actually learn, the different learning paradigms.
Right, and we can really group them into 4 main approaches, starting with the one that, built the modern AI boom, supervised learning.
This is the one that needs all that perfectly labeled data we talked about, right? Where there's a teacher in the room.
Always a teacher. The system is learning to map an input, like a photo of a dog, to the correct label, dog. And it's a closed loop. The key is the error metric.
Right.
The model makes a guess. Let's say it guesses cat. It compares that to the right answer, dog. The difference between them is the error. And that error signal is fed back into the system, telling it how to adjust its internal knobs and dials to get closer to dog next time. It's very efficient for a lot of tasks.
Then we have the opposite, where the system is on its own, unsupervised learning.
Exactly. Here, there are no labels, no right answers. The goal is just discovery. Finding hidden patterns or structures in the data just by looking at it. It's really important for things like customer segmentation. For instance, finding groups of similar customers without knowing beforehand what those groups might be.
And what are the main ways it does that?
Clustering is a big one, just grouping similar data points together. Another cool one is Hebbian learning, which is based on a neuroscience principle. Neurons that fire together, wire together. Basically, if 2 nodes in the network are active at the same time, the connection between them gets stronger. It's slower than supervised learning, but it's essential when you're exploring a new, unmapped territory of data.
Okay, the third paradigm seems to be everywhere now, especially with robotics and games, reinforcement learning.
Reinforcement learning is all about teaching an agent, a robot, a game-playing AI, how to act in an environment to maximize some kind of reward. The key difference is it doesn't get the right answer like in supervised learning. It just gets feedback, a good job or a bad job.
So it's basically structured trial and error. This sounds a lot more like how people learn.
It is much closer to how we learn. The system gets a reward for good moves and a penalty for bad ones. There's even a biological link. The math behind it mirrors how dopamine works in our brains. And it creates this classic trade-off, exploration versus exploitation. Do you stick with what you know works okay, or do you try something new that might be way better or way worse?
And because the feedback is so simple, just yes or no, it's a slower process.
Much slower, but incredibly powerful for learning in dynamic, changing environments.
And that leaves the last one, which is sort of a hybrid, active and semi-supervised learning.
This is all about being practical. Labeling data is really, really expensive. So semi-supervised learning tries to use a tiny bit of expensive labeled data alongside a huge pile of cheap, unlabeled data to get better results.
And active learning is about being smart with the human labeler's time.
Exactly. The model itself gets to choose which data points it's most confused about and asks the human for a label for just those. It doesn't waste time on the easy stuff it already knows. There's a great approach called query by committee, where you have several models vote, and if they all disagree on an example, that's the one you send to a human. It's incredibly efficient.
So once the model has learned through one of these methods, it has to store that knowledge. Which brings us to the 5th block, the knowledge base.
The knowledge base is the system's memory. It's what makes sure the past learning affects future behavior. In old AI systems, this was like a literal database of facts and rules.
But with deep learning, it's not like that, is it? The knowledge isn't in a neat little file somewhere.
It's a much deeper kind of storage. We call it implicit knowledge. The information isn't in a single place you can point to. It's spread out, encoded in the strengths of the millions of connections between all the neurons in the network. The network is the knowledge base. The model is the memory.
That's a really important distinction. Okay, let's circle back to the theory, because with all this power comes a big risk. The risk of the model just memorizing the data instead of learning from it. This is the whole issue of generalization versus overfitting.
And generalization is the ultimate goal. Can the model make good predictions on data it's never seen before? Overfitting is the biggest failure mode. It's when the model learns the training data perfectly, including all the random noise and weird quirks that are only in that specific data set.
So the training score looks great, but it falls apart in the real world.
Exactly. The error on the training data keeps going down, but the error on new, unseen data starts to shoot up. It's learned the wrong lessons.
How do engineers prevent that?
A classic technique is early stopping. You watch both the training error and the error on a separate validation set. At some point, the validation error will stop decreasing and start to creep back up. That's the moment you stop training, even if the training error could go lower. You stop right at that sweet spot of best generalization.
And this whole balancing act is guided by the bias-variance trade-off. That's a term you hear a lot. Can you break that down for us?
Okay, think of it like drawing a map. The total error in your model comes from two main sources, bias and variance. Bias is the error you get from your map being too simple.
Like trying to navigate a city with a map that only shows major highways.
Perfect analogy. A high bias model is too simple. It misses the underlying complexity in the data. Variance, on the other hand, is the error from your map being too sensitive to the specific data you use to draw it.
So a map that includes every single car that was parked on a street on one specific Tuesday, it's not going to be useful on Wednesday.
Exactly. You're always trading them off. A simple model has high bias but low variance. A very complex model, one that overfits, has low bias on the training data but super high variance. The art is finding the right level of complexity in the middle.
And to control that, engineers use techniques like dropout. How does just randomly turning off neurons help?
It's a really clever idea.
Yeah.
It's designed to stop something called co-adaptation. That's when certain neurons become too dependent on each other. Like, neuron A only knows how to work if it gets a specific signal from neuron B. It makes the network fragile.
They become lazy specialists.
They do. So dropout, during training, just randomly switches off some neurons for each training example. This forces every single neuron to learn to be more robust, to pull its own weight, because it can't rely on its neighbors always being there. It creates a much more resilient and generalized network.
Now, this is where things get really weird and challenge everything we thought we knew. The double descent challenge.
This is a wild, recent discovery that turns decades of theory on its head. The classic idea was that as you make a model more complex, error goes down, hits a sweet spot, and then shoots back up as you enter the overfitting zone.
Right. Don't make the model too big for your data.
But double descent shows that if you just keep making the model bigger, way past that point where it should be overfitting horribly, something strange happens.
What happens?
The error starts to go down again. These massively over-parameterized models with way more parameters than data points can perfectly memorize the training data and still generalize beautifully to new data.
Wait, so the old wisdom is wrong. Bigger isn't always worse.
It seems to be incomplete, at least. The theory is that once a model is big enough, it has so many possible solutions. It can find one that not only fits the data perfectly, but is also somehow simple and smooth, which helps it generalize. It's why just scaling up these huge language models works so well, and it kind of breaks all the old rules.
So we've covered learning, memory, and the wild theory behind it. The last piece of the puzzle is putting it all to work. System integration and human AI orchestration.
Right. This is where we get practical. The platform is your basic infrastructure, the hardware and software. And you have to think about your development systems versus your live operational ones. They have very different needs.
And integration means more than just plugging it in. It's about making it fit into the system of systems.
That's the key phrase. You have to decide. Does the AI run at the edge on a phone or a drone where it has to be fast but simple? Or does it run in the cloud, where it could be huge and complex, but there's a time delay? You have to think about connectivity, computing power, the whole pipeline.
And it gets even more complex when a human is involved. Tell me about human autonomy teaming.
This whole field is about how people and machines can work together safely and effectively. The main goal is to make sure the human always has meaningful control, especially when the stakes are high.
But you mentioned a risk that I think a lot of people miss, the risk of the AI being too good.
It's a classic human factors problem. If the AI does all the interesting hard work and the human's just left to watch a screen, they get bored, they lose focus. And performance can actually go down because the human isn't engaged and they might miss the one rare time they actually need to step in.
So you have to design the job to keep the human in the loop in a meaningful way.
You do.
And to structure all these complex interactions, there's a new concept called flows. What are they, and how are they different from a normal software pipeline?
Flows are a really powerful new way to think about this. They're like modular building blocks for computation. You can have an atomic flow, which is just one simple task query a database, call a language model, ask a human a question.
Like Lego bricks.
Exactly like Lego bricks. And then you build composite flows by snapping those atomic flows together in complex ways. The beauty is that it's all modular. You can build these incredibly sophisticated multi-agent processes without writing one giant, fragile piece of code.
Give me a real example. How would a composite flow work?
Okay, imagine you're trying to solve a hard coding problem. The flow might be: first, an atomic flow calls an AI to generate code. Then a composite flow kicks off to execute tests on that code. If the tests fail, a whole different debug failure flow starts up, which itself might call other tools to analyze the error, suggest a fix, and then rerun the test. This is like an operating system for AI agents.
And you mentioned humans can be a block in this system too.
That's the most powerful part. You can treat a human expert as just another computational block. Studies have shown that for really novel problems like these coding challenges, if you just have a human provide a short, high-level plan at the very beginning.
Like an oracle plan.
An oracle plan, yeah. If you feed that into the flow, the system's success rate goes up dramatically.
How dramatically?
In some cases, we've seen solve rates increase by over 50 percentage points on problems the system has never seen before. It proves that designing these smart collaboration structures, these flows, is strategically critical. It lets you combine the best of human insight and machine speed.
So we've come all the way from raw data to this sophisticated orchestrated system, which brings us to the final block, the whole point of it all, information output.
The output is the value, and it comes in so many forms now. You have natural language generation, which is the reverse of understanding turning structured data back into human language. This is chatbots, an AI writing a financial report from sales numbers.
And then there's the output that actually affects the physical world.
That's robotics. This is where the AI uses everything it's learned to physically move and interact with the environment. Autonomous cars, manufacturing robots, warehouse automation. The information output is a real physical action.
So we've done the full loop. Data gets pre-processed. It's shaped by these deep learning algorithms stored in this weird implicit knowledge base, and then finally gets integrated into a system governed by flows to deliver a valuable output.
It's a dense ecosystem, but it is structured. And the really critical thing to get is that the improvements in these core blocks, the learning, the reasoning, they're not linear. They're accelerating. And that has huge strategic implications for everyone.
So if you're a manager watching this, what should you be focused on?
You should be focused on one thing: competence-destroying innovations. For a long time, technology, including AI, was competence-enhancing. It made skilled people better at their jobs. But as these core components get more powerful, we're moving very quickly toward AI that makes entire human skill sets obsolete.
It's not just helping you do the job, it's doing a job instead of you.
Exactly. Think about autonomous trucks replacing drivers, or AI systems that can do the complex work of a specialized media buyer. Understanding these building blocks, how they learn, what data they need, how they're architected, isn't just a technical exercise. It's strategic survival. It's about anticipating these huge shifts.
That's the real challenge, isn't it? Understanding these components is the first step toward preparing yourself and your company for a future where your core skills might not just be enhanced, but completely replaced.
Every executive needs to be asking, will my current business model and my people skills be able to exploit this technology, or will they be devalued by it? And you can only answer that if you have a clear component-level understanding of what's actually happening under the hood.
Thanks for listening to the Adaptix podcast. If you have any questions, feel free to reach out to us.